So let's now discuss the cardiac cycle. And the cardiac cycle is a series of events of blood flow and pressure changes that occur as the heart pumps out blood. And some key terms to know here are systole, which refers to contraction of the atria or ventricular muscles, and diastole, that refers to contraction or relaxation of the atrial or ventricular muscles. These two terms are used when we refer to blood pressures. The upper number is the systolic pressure. The diastolic pressure is the lower number, as in 120 over 80. 120 would be systolic pressure, 80 would be diastolic pressure. Another key term that's important to know here is end diastolic volume, which is the volume of blood remaining in the ventricle at the end of ventricular relaxation or diastole, and end systolic volume, which would be the volume of blood that remains in the ventricle after contraction of that ventricle or after systole of that ventricle. So question number 15 is to fill out this chart that you'll be able to find on Blackboard that goes through and asks you to give details of several events that occur during the cardiac cycle as follows. So during the cardiac cycle, there are three major phases. The first one is ventricular filling. Ventricular filling refers to that phase in mid to late relaxation of the ventricles during which they're filling, and at the very end of ventricular filling, we see contraction of the atria, but that accounts for a minimal flow of blood. Most of the flow of blood into the ventricles during this first phase is due to the pull of gravity on blood from the atria to the ventricles. The second phase is ventricular systole, which refers to stress or contraction of the ventricles. And in this phase, we also see relaxation or diastole of the atria. Now, this particular phase is divided into two pieces: isovolumetric contraction and ventricular ejection. During isovolumetric contraction, we see that both the AV and the SL valves are closed. The ventricles reach their optimal volume, and then at the end, those ventricles eject or contract to eject the blood that's in them. The last phase is early diastole of the ventricles. That's early relaxation of the ventricles, during which they begin again to fill with blood. So again, during ventricular filling that occurs in mid to late diastole, as we can see here on the EKG, occurs because the atria are allowing blood to flow through those AV valves, the tricuspid on the right, the mitral valve or bicuspid on the left, using gravity into the ventricle. So the pressure in the ventricle is fairly low, but we see that the end diastolic volume is increasing. At the end of ventricular filling, the atria contract so that they eject the last bits of blood in them into the ventricles, and at that point the atrioventricular valves would obviously be open, and the pulmonary and aortic semilunar valves, those that guard the entrances to the pulmonary trunk and the aorta respectively, are closed so that there's no leaking of blood into those vessels. And at that point, when the AV valves close, we hear the first heart sound. The second phase, ventricular systole, at the end, we see atrial diastole. But during ventricular systole, we see that the ventricles are filling with blood. And at close to the end, right before ventricular ejection, we see the dicrotic notch. And the dicrotic notch occurs because of closure of both the AV and the semilunar valves. The semilunar valves being louder, we hear the second heart sound. And then we see ventricular ejection, which refers to contraction of the valves, contraction of the ventricular myocardium, and ejection with that QRS wave of blood into the aorta. Once enough pressure has been generated in those ventricles, it forces the SL valves open and blood's ejected. And then we see the third phase, early diastole or early relaxation of the ventricles. The aortic and pulmonary semilunar valves once again close so blood can't escape from those two lower chambers. The AV valves are open and will continue to open more as more blood pours into them and causes a gravitational pull of blood from the atria to the ventricles. Now, in the midst of the second phase, we see stroke volume. Stroke volume refers to the amount of blood that's ejected from the heart with each heartbeat. Cardiac output is the multiplicand of heart rate times stroke volume, where heart rate refers to pulse or the number of beats that the heart does per minute, and stroke volume, which is the amount of blood ejected by the ventricle, the left ventricle, with each heartbeat. Normally, cardiac output should be about 5 to 5.25 liters per minute. That's about the entire volume of your body's blood. In a person who is quite fit, a trained athlete, that cardiac output can increase to about 35 liters per minute because when the heart is worked, when it's conditioned, the myocardium grows stronger and the stroke volume will increase considerably even though heart rate goes down a bit. And two vital pieces within that, or that determine stroke volume, which also determines cardiac output, are the end diastolic volume and the end systolic volume. And we see these back in the cardiac cycle, where end diastolic volume is the amount of blood that remains in the ventricle after filling, and end systolic volume is the amount of blood that remains in the ventricle after ejection. So the healthier the heart muscle, the lower the end systolic volume should be. Question 16. For cardiac output, 16A, define cardiac output and its normal value. 16B, give the formula for cardiac output and define all of the variables with their correct units. Question 16C, how does cardiac output change in an athlete who's trained? Number 17, for stroke volume, define stroke volume and its normal value. 17B, give the formula for determining stroke volume and define the variables with their units. Question 17C, list the three main factors that affect stroke volume and explain those factors. And here's the answer to 17C. When it comes to stroke volume, that's the amount of blood ejected by the ventricles per heartbeat, per heart contraction. That is end diastolic volume, meaning the amount of blood that's in the ventricle before contraction, minus end systolic volume, the amount of blood that's left after contraction. And that's dependent on three main factors: preload, contractility, and afterload. Now, preload, according to the Frank Starling law, says that the degree of stretch of cardiac muscle before they contract has an effect, or meaning that the longer the muscles are stretched, the more force they generate with contraction. So the more blood that's returned via venous return, meaning return of blood from the venous system, the stronger preload is, and the more blood that's ejected, so that would decrease end systolic volume. Contractility refers to the strength of the myocardium. How strong is that cardiac muscle? That contractility is increased by calcium influxes, by sympathetic stimulation that increases the rate and force of contraction of the myocardium, and by hormones such as thyroxine, glucagon, epinephrine, and medications such as digitalis. It's decreased by excess calcium or calcium channel blockers or beta blockers, even acidosis that might occur as in emphysema. In those cases, heart rate would slow down and the muscles in the body organs get less oxygen. Afterload, the third factor that affects stroke volume, is the pressure that the ventricles have to overcome to get blood into the aorta and to the rest of the body. So in the case of something like hypertension, meaning excess pressure in the heart and around the heart, where the myocardium is working harder to, say, overcome an occlusion in a vessel, say the aorta or future vessels, atherosclerosis maybe, that problem increases the amount of blood left in the ventricle after ventricular systole, that's the ESV, and thus reduces the stroke volume. Question number 18. How does preload affect stroke volume? And your answer should include discussion of the Frank-Starling law and venous return. 19. Describe factors that increase or decrease contractility. 20. What is afterload and how is an increase in afterload related to cardiac output and stroke volume?